Recommended texts for an industrial wiring course include Electrical Wiring Industrial, 16th edition by Stephen L. Herman and Dale R. House, Industrial Electrical Wiring Residential, Commercial, Industrial, and Special Applications by Rex Miller, NFPA 70 National Electrical Code 2023, which is the latest edition, Industrial Power Distribution and Motor Control by James E. Traster, and Plant Electrical Systems Maintenance, Troubleshooting, and Safety by Daniel R. Schleier. These texts cover a wide range of industrial wiring topics. Firstly, fundamentals including basic electrical theory, safety, codes, and materials. Secondly, hazardous locations that include classification of hazardous areas, wiring methods, and equipment requirements. Thirdly, hospitals, which include electrical safety standards, emergency power systems, and patient care equipment. Fourthly, fire and emergency systems that include fire alarm, sprinkler systems, emergency lighting, and backup power. Fifthly, generators and uninterruptible power supply systems, which include emergency power generation, UPS systems, and maintenance. Sixthly, hooking up new machinery including load calculations, motor connections, and control circuits. Seventhly, generating new voltages and frequencies including transformers, frequency converters, and equipment testing. Eighthly, chemical plants covering explosion-proof equipment, grounding, and special wiring practices. Ninthly, lightning protection including surge protection devices, grounding systems, and structural protection. A facilities wiring course provides a comprehensive understanding of industrial wiring regulations and practices. It prepares students for real-world electrical work in various industrial settings. This course enhances the skills of self-taught individuals and fills gaps in knowledge. It facilitates the coordination between electrical engineers, facility managers, and maintenance personnel. The National Electrical Code, or NEC, is a regionally adoptable standard for the safe installation of electrical wiring and equipment in the United States. It is part of the National Fire Code series published by the National Fire Protection Association, or NFPA. While not itself a law, the NEC is often adopted by states and municipalities in an effort to standardize their enforcement of safe electrical practices. In such cases, it is given legal authority by the adopting jurisdiction. The NEC is updated and published every 3 years. The term code means a standard that is an extensive compilation of provisions covering broad subject matter. The NEC contains requirements for electrical installations in buildings and other structures. It covers topics such as wiring methods, overcurrent protection, grounding, and equipment installation. It is important to note that the NEC is not a design guide. It provides minimum safety requirements, but it does not tell you how to design an electrical system. That is the responsibility of a qualified electrical engineer. The NEC is divided into chapters, articles, and sections. Chapters are the broadest divisions of the code. Articles cover specific subjects such as wiring methods or grounding. Sections are the smallest divisions of the code and contain specific requirements. The NEC is also divided into parts. Parts are used to group related sections together. For example, Part 1 of Article 250 covers general requirements for grounding and bonding. It is essential to understand the structure of the NEC in order to find the information you need. The NEC is a complex document, but it is essential for anyone who works with electrical systems. By understanding the NEC, you can help to ensure that electrical installations are safe and compliant with applicable codes and regulations. Hazardous locations are classified based on the type of hazardous material present and the probability of it being present in an ignitable concentration. The NEC defines hazardous locations in Article 500. These locations are classified into classes, divisions, and groups. Classes define the general nature of the hazardous material, such as flammable gases or combustible dusts. Divisions indicate the probability of the hazardous material being present in an ignitable concentration. Groups further categorize the hazardous material based on its specific properties. Class allocations are those in which flammable gases or vapors are, or may be, present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class Roman II locations are those in which combustible dust is, or may be, present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class Roman III locations are those in which ignitable fibers or flyings are present, but not likely to be in suspension in the air in quantities sufficient to produce ignitable mixtures. Division I locations are those in which the hazardous material is present under normal operating conditions. Division II locations are those in which the hazardous material is present only under abnormal operating conditions, such as equipment failure or rupture of a container. The group classification further defines the specific hazardous material. For example, Class I group includes acetylene, while Class I Group B includes hydrogen. Understanding the classification of hazardous locations is crucial for selecting the appropriate wiring methods and equipment. Wiring methods in hazardous locations must be designed to prevent the ignition of the hazardous material. This can be achieved by using explosion-proof enclosures, intrinsically safe circuits, or other methods. Equipment used in hazardous locations must be specifically listed and labeled for the class, division, and group of the location. This ensures that the equipment is designed and tested to withstand the specific hazards present in the location. Hospitals have unique electrical requirements due to the critical nature of patient care. The NEC contains specific requirements for hospitals in Article 517. These requirements address electrical safety, emergency power systems, and patient care equipment. Electrical safety is paramount in hospitals to protect patients and staff from electrical shock hazards. Article 517 requires that all electrical equipment in patient care areas be grounded to minimize the risk of electrical shock. It also requires the use of ground fault circuit interrupters, or GFCIs, in certain locations to further reduce the risk of electrical shock. Emergency power systems are essential in hospitals to ensure that critical equipment continues to operate during power outages. Article 517 requires that hospitals have emergency power systems that are capable of providing power to essential electrical systems, such as life support equipment, operating rooms, and critical care areas. These emergency power systems must be tested regularly to ensure that they are functioning properly. Patient care equipment must be designed and installed to minimize the risk of electrical shock and other hazards. Article 517 contains specific requirements for the wiring and grounding of patient care equipment. It also requires that patient care equipment be regularly inspected and tested to ensure that it is safe to use. Fire and emergency systems are critical for protecting life and property in the event of a fire or other emergency. These systems include fire alarm systems, sprinkler systems, emergency lighting, and backup power. Fire alarm systems are designed to detect fires and alert occupants of the building. These systems typically include smoke detectors, heat detectors, and manual pull stations. Sprinkler systems are designed to suppress fires and prevent them from spreading. These systems typically include a network of pipes and sprinklers that are activated by heat. Emergency lighting is designed to provide illumination during power outages. This lighting is typically powered by batteries or generators. Backup power systems are designed to provide power to essential equipment during power outages. These systems typically include generators or uninterruptible power supplies. Generators and uninterruptible power supply systems are essential for providing emergency power to critical equipment during power outages. Generators are typically used to provide backup power to entire facilities, while UPS systems are typically used to provide backup power to individual pieces of equipment. Generators are typically powered by diesel fuel, natural gas, or propane. They are equipped with automatic transfer switches, or ATSs, that automatically switch the load from the utility power to the generator power in the event of a power outage. UPS systems are typically powered by batteries. They provide a seamless transfer of power from the utility power to the battery power in the event of a power outage. This ensures that critical equipment continues to operate without interruption. When hooking up new machinery, it is important to perform load calculations to ensure that the existing electrical system can handle the additional load. Load calculations involve determining the total amount of power that the new machinery will draw. This information is used to determine the appropriate size of the circuit breakers, conductors, and transformers that will be needed to supply power to the machinery. Motor connections must be made in accordance with the manufacturer's instructions and the requirements of the NEC. A NEC contains specific requirements for the wiring and grounding of motors. Control circuits are used to control the operation of machinery. These circuits typically include push buttons, switches, relays, and other control devices. When generating new voltages and frequencies, transformers and frequency converters are used. Transformers are used to step up or step down voltages. They are essential for matching the voltage of the power supply to the voltage requirements of the equipment. Frequency converters are used to change the frequency of the power supply. They are essential for testing equipment that is designed to operate at different frequencies. Equipment testing is performed to ensure that the equipment is operating properly and safely. This testing typically involves measuring voltage, current, resistance, and other electrical parameters. Chemical plants have special electrical requirements due to the presence of hazardous materials. Explosion-proof equipment is used to prevent explosions in areas where flammable gases or vapors are present. This equipment is designed to contain any explosions that may occur within the enclosure. Grounding is essential in chemical plants to prevent the buildup of static electricity. Static electricity can ignite flammable materials and cause explosions. Special wiring practices are used in chemical plants to minimize the risk of electrical hazards. These practices include the use of sealed conduits, explosion-proof fittings, and other specialized equipment. Lightning protection is essential for protecting buildings and equipment from lightning strikes. Surge protection devices are used to protect electrical equipment from voltage surges caused by lightning strikes. Grounding systems are used to provide a path for lightning current to flow to ground. Structural protection is used to protect buildings from physical damage caused by lightning strikes. A facilities wiring course provides a comprehensive understanding of industrial wiring regulations and practices. It prepares students for real-world electrical work in various industrial settings. It enhances the skills of self-taught individuals and fills gaps in knowledge. It facilitates the coordination between electrical engineers, facility managers, and maintenance personnel. A strong understanding of electrical theory is crucial. This includes Ohm's law, which describes the relationship between voltage, current, and resistance. Understanding series and parallel circuits is also important for analyzing and troubleshooting electrical systems. Knowledge of alternating current and direct current principles is essential for working with different types of electrical equipment. Safety is paramount when working with electricity. Always to energize circuits before working on them. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to prevent accidental energization of circuits. Be aware of potential hazards such as arc flash and electrical shock. The NEC provides a comprehensive set of guidelines for electrical installations. Familiarize yourself with the NEC and follow its requirements. Obtain the latest edition of the NEC and keep it readily available for reference. Understand the different articles and sections of the NEC and how they apply to specific situations. Consult with a qualified electrical inspector to ensure that your installations comply with the NEC. Different types of wiring methods are used in industrial settings. Conduit is a rigid metal or plastic tube that protects conductors from damage. Cable trays are used to support and route cables. Wireways are enclosed channels that provide protection and routing for conductors. Each wiring method has its own advantages and disadvantages, and the appropriate method will depend on a specific application. Various types of electrical materials are used in industrial wiring. Conductors are used to carry electrical current. Insulation is used to protect conductors from short circuits and ground faults. Connectors are used to join conductors together. Fittings are used to connect conduit and other wiring components. Selecting the appropriate materials is essential for ensuring the safety and reliability of electrical installations. Load calculations are essential for determining the appropriate size of circuit breakers, conductors, and transformers. Calculate the total load of all equipment that will be connected to the circuit. Consider factors such as motor starting currents and demand factors. Use the NEC to determine the appropriate ampacity of conductors and the size of circuit breakers. Motor connections must be made in accordance with the manufacturer's instructions and the requirements of the NEC. Identify the motor's voltage, horsepower, and full load amps. Select the appropriate wiring method and conductor size for the motor's current rating. Connect the motor's terminals to the appropriate power supply conductors. Control circuits are used to control the operation of machinery. Understand the function of each component in the control circuit. Use appropriate wiring methods and materials for the control circuit. Test the control circuit to ensure that it is functioning properly. Transformers are used to step up or step down voltages. Understand the transformer's voltage ratio and kVA rating. Select the appropriate transformer for the application. Connect the transformer's primary and secondary windings to the appropriate power supply conductors. Frequency converters are used to change the frequency of the power supply. Understand the frequency converter's input and output voltage and frequency ratings. Select the appropriate frequency converter for the application. Connect the frequency converter's input and output terminals to the appropriate power supply conductors. Perform regular maintenance on electrical equipment to ensure that it is operating properly and safely. Inspect equipment for signs of damage or wear. Clean equipment to remove dirt and debris. Lubricate moving parts. Test equipment to verify its proper operation. Grounding is essential for preventing electrical shock hazards. Ground all electrical equipment to provide a path for fault current to flow to ground. Use appropriate grounding conductors and connections. Test the grounding system to ensure that it is functioning properly. Surge protection devices are used to protect electrical equipment from voltage surges. Install surge protection devices at the service entrance and at sensitive equipment. Select surge protection devices with appropriate voltage and current ratings. Inspect surge protection devices regularly to ensure that they are functioning properly. Explosion-proof equipment is designed to contain any explosions that may occur within the enclosure. Select explosion-proof equipment that is listed and labeled for the specific hazardous location. Install explosion-proof equipment in accordance with the manufacturer's instructions. Inspect explosion-proof equipment regularly to ensure that it is in good condition. Special wiring practices are used in chemical plants to minimize the risk of electrical hazards. Use sealed conduits to prevent the ingress of hazardous materials. Use explosion-proof fittings to connect conduit and other wiring components. Follow all applicable codes and regulations for wiring in hazardous locations. Lightning protection systems are designed to protect buildings and equipment from lightning strikes. Install lightning rods on the roof of the building. Connect the lightning rods to a grounding system. Use surge protection devices to protect electrical equipment from voltage surges caused by lightning strikes.